some stuff in here that if you've seen me talk about this before will be old news, but there are a lot of people I think who haven't. Yeah, so. Okay, so David showed this earlier. We're trying to automate force field parameterization.
Semi-automated.
Yes, with a semi-automated weapon. So I'm particularly interested in how we go about automating the chemical perception associated with that. So how does the force field decide that your aromatic bond is different than your single bond? And as David talked about, we have that direct chemical perception now that separates that from not being atom types. However, Smirnoff 99 Frost still had a wizard, and maybe a mini wizard, since I've made a lot of changes since Chris wrote the initial one. So we want to move away from that writing SMIRKS patterns by hand. So this is basically the process you want to follow. We want to do the same thing that the wizard was doing by hand, but have the computer learn that process instead. So it needs to be able to create new SMIRKS patterns. Sounds easy, but was a fairly complicated first step. Needs to be able to compare to reference data and decide, and then make decisions about if you need new chemical perception or if there's more parameters there than what we actually need to represent the data you have. So as a first step, we decided to try to test this process and compare it to reference force fields. So just can we generate the same chemical complexity that exists in Smirnoff 99 Frost or in permafrost? Okay, so like I said, the first step in all of this is can we make changes to SMIRKS patterns, which are just strings, but they're very complicated strings. So we've created a new Python object that we've called chemical environments that basically separates the SMIRKS pattern into the way a chemist might think about a chemical fragment. So it has atoms connected by bonds that can connect to other atoms using network X. So it bridges those atoms, and then it can make changes on the decorators on atoms. It can combine atomic numbers. I'm going to walk through just like a couple of basic SMIRKS patterns. So it can get as easy as just anything. Any atom connected by any bond to any other atom. The numbers indicate how many key atoms are in that step. So I think David talked about that a little bit earlier, but in that case that's a bond because it has two atoms that are labeled. You can add atomic numbers, we can add complexity, including things like ors, so you can you don't necessarily have to have it based on just a single element, so you can have carbon or nitrogen, and this is a single bond, the semicolon is an and in a ring. This will get even more complicated.
It doesn't matter, you just equally valid to put a C or a #6.
Yeah, so in the letters, a capital letter indicates aliphatic and a lowercase letter indicates aromatic. So for our purposes, we've largely been using the element numbers and then a decorator that indicates if it's I don't have it on here, but there's also a decorator letter that you can use to indicate aliphatic versus aromatic. So we have those isolated instead of trying to pick a letter and have it make both of those decisions. But the parsing capability can handle either one if you hand it. If someone was going to go in and go, I want to make my own parameter and write a SMIRKS pattern, Smirnoff could still use it either way.
What's the best way to get up to speed on SMIRKS for the people, or smarts for the people who aren't?
It really is like learning a new language. So I think we have a lot of notebooks in the Open Force Field GitHub where you can put in a SMIRKS pattern and then visualize it, and it'll highlight on the molecule where that SMIRKS pattern is. I think that's the easiest way to like make sure your understanding matches.
Yeah.
There's an OpenEye cheat sheet.
And then there's an OpenEye cheat sheet that I can send the link to the documentation. Awesome. It's in a few different places on the Slack, but I can pin it somewhere.
The Daylight page was not as informative.
The OpenEye
There's a
page.
demo page where you can put in strings and it'll show you what it represents, and you can keep playing it.
Oh,
got it. Okay, that might be
I've
more.
not
what you're
found
putting in
that
your
one.
smarts to.
Can you post the link for
Yeah,
that?
could you
Sure,
just
I'll
yeah,
find it.
or send it to somebody. Yeah, I think the more you can look like and it's all of the like logical combinations that if you haven't done logical Boolean additions in a while, sometimes those don't work quite the way you thought they were going to. They get remarkably more complex than this, but this is sort of the level that most of Smirnoff is working on. I actually made that one up, so it might be more complex. Since we're not. It's okay, don't worry about it. Okay, so David showed this earlier, so I'm going to go through it a little more quickly. But basically, we then can make choices about how we change those SMIRKS patterns. We can add atoms, move atoms, add decorators to the atoms or the bonds. So I'm going to work through just an example of that so I can show scoring with the same example that we show choices on. So we start with an initial list of parameters. In this world, I only care about carbon-carbon bonds. So there's only one thing in my parameter list, so it can't delete it. So we're going to choose to make a new one. It's going to arbitrarily decide to change bond. And then this dot, the colon means it's aromatic. So now our list has two things in it. It has the initial generic carbon-carbon bond and an aromatic carbon-carbon bond.
Is there a part where you check if the change is still chemically valid?
Yes.
So is that's after somehow change a decorator,
Yeah, so,
but before add it to the list? Like if
right,
you wanted to
yeah,
have 5 bonds between those 2 carbons or something.
So there's, it works similar to other, maybe not all, it's a reversible Monte Carlo algorithm. So it makes a current list of parameters and then checks a couple of things, and if the checks fail, it fails the step, and then it evaluates the score and decides to accept or reject
Are the
it.
checks like valid chemistry, or are there somehow energy terms associated with?
So there's not energy, the scoring sort of has
Yeah.
energy in quotes.
Right. I meant
Energy because
in
that's how we
quotes.
think about Monte Carlo.
Right.
So the valid checks include if the new one doesn't match anything in your molecules, then it gets rejected because it's not.
It's useless.
It's
Right.
not. Yeah, it's useless. There is it runs and is valid. It just it checks that this new SMIRKS pattern is parsable, but given the way we're making moves, it shouldn't generate something that's not parsable because you can write a SMIRKS pattern for something that's not chemical. But at this point, I'm trying to remember, it's been a while since I looked
If
at
it
all
steals
of those.
all of the molecules from its parent,
Yeah.
then its parent is useless,
Right,
and then it's
so-
rejected.
We allow for a generic base type that can be empty, but beyond that, so if we were gonna all of your carbon-carbon bonds were aromatic.
Wait, hold on.
this-
If it steals from its parent, so wouldn't a wild card steal from its parent, and then you just end up with wild cards?
So the typing is meant to be hierarchical,
Yeah.
right? So it's always making something that's more
Yeah,
refined than
more
its parent,
specified.
that has more things on it. It's
Okay.
more specific.
Okay,
But if
so
it's so specific that it just still types all of the things that its parent had, it's not doing anything
It's not
useful.
useful.
So it's not any more specific in
So
any useful
these
way.
get rejected or the parents get rejected?
The new
The new one
proposed.
gets
The
rejected.
new one gets
Yeah.
rejected.
So the move is always about either can I delete the thing I deleted, or can the new thing that's being added be valid? So you also if you were to delete a parameter and then not all of your bonds are typed, it won't let you delete it because everything needs to have something assigned to it. Yeah. I think there's some. Yeah, we'll get to this being inefficient and me thinking you might need to be able to do multiple steps at a time later. So I'm going to follow through that same example to just talk about scoring. So when we're talking about reference force fields, we make a list of the, in this case, bonds in your molecules, and each bond gets assigned a label from your reference force field and a label from your current list. So my current list now just has one bond in it, but on my test molecule, I have aromatic bonds and I have single bonds, so it has 2 types in the reference force field. So we have a reference set, we type it with our current set, but when we're scoring, we're only going to keep one pair connection. So this one bond can't match both of them because the goal is to get the same chemical complexity or the same splitting that we got in the reference force field. And it uses a bipartite algorithm that keeps the highest matching one only. So that's why there's no match on this one. So right now we only score a 6 out of 9. And then when we add our aromatic bond, right, so now we have a current set label that matches each of our reference sets, and then you get a total score. So that's a simplistic example, but it at least gives an idea of how the scoring is working. So one of these things that we've been showing up until the heat map that David showed today is that we can plot the score or how well our generated SMIRKS patterns matches against a reference, which in this example, we do have these are temperatures in the sense that they control how random the Monte Carlo algorithm is. It's not a simulation, so there's no physical temperature behind it. So in this example, we do happen to get to iterations where there is 100% agreement, But as David showed with the heat maps earlier, there are also situations where we might never find all of the reference parameter types in one iteration, but we do find things that agree with them throughout a simulation, which is sort of the point of Monte Carlo, is that you can get a distribution. So how do we think about distributions when we're thinking about SMIRKS patterns? Like, they're not an energy distribution. So how do we find and isolate those SMIRKS patterns is an ongoing question in how to do it practically when I'm not just saying find the ones that are 100% compared to the reference force field. Okay, so I'm just going to walk through an example on how hard what might look like a relatively simple SMIRKS pattern is to find using those steps. Okay, so right now when we're searching for torsions, we start everything with the center bond specified with just element numbers. So there's any bonds between all of them that you know it's a carbon and a nitrogen. So in one of my last runs of simulations, this is a torsion that I wasn't able to find. So we look at the changes that were made. There are 4 new bond decorators. So this one is single or aromatic, double, single, and there are 2 atom decorators added. So that carbon is supposed to be an X3, and that nitrogen is an X2. Okay. So just to look at the probability of creating any one of those steps. And this is looking at generating this SMIRKS pattern exactly, which isn't necessarily what we need to be able to do. We need to be able to generate chemical complexity. We in theory might be able to find a SMIRKS pattern that's equivalent but not identical. But assuming we want to find the identical one, you have to take into account the probability of picking this parent to generate a new child from this is a rough, assuming you have about 50 to start, but the torsion lists get rather large. And then I rounded the odds of making any one of those decisions to about 0.01, which works out to needing about 1 million SMIRKY moves to generate that one SMIRKS pattern.
That's 1 billion.
That is 1 billion. I copied it off my calculator without.
Well, so
Okay.
the good news is that parallel Monte Carlo moves,
Mhm.
essentially, when we're in the low acceptance
Yeah.
rate regime, right, can speed things up by as much as you can do in parallel at
Okay.
once.
Yeah, so so there's basically what the point of this is that while we've been able to show that we can generate a lot of chemical complexity, there's certainly some efficiency that needs to be added back in now that we have an algorithm that's working. Okay, so my next steps is trying to move away from comparing to a reference force field, because we don't want to just recreate Smirnoff 99 Frost. We want to be able to make new parameters. So I've been thinking through how to do that, and we've talked about this a little bit on phone calls with people who are in those, but the idea is that it'll follow a similar algorithm to what we were doing before, but instead of comparing to a reference force field, you'll compare to a distribution of whatever property you're looking at, so distribution of Leonard-Jones parameters, or bonds, or torsions, or angles. Sort of just talked about that. I think I covered most of that. Okay, so my initial idea with this was I'll just start with the most simple. We're just going to go to hydrocarbons, throw out alkyl OH, and only look at things around the carbons. Sort of ignore the hydrogens for right now, although I do have angles that involve the hydrogens. So I have some distributions that I've been considering that are angles around carbon atoms and bond lengths around carbons, between carbons, carbon-carbon bond lengths. But basically it brings up a lot of these questions like what John was talking about earlier, that you can Bayesian infer how many distributions you have. Should we somehow, so basically we need to be able to identify how many distributions there are if we're going to use that scoring algorithm.
Where the bond lengths are coming from quantum optimized?
Yeah, so
Okay.
these, Vicky's going to talk about her pipeline later, but it was a relatively low-level QM calculation just to have some data to play with that was at least real QM data versus like me making up distributions.
That ANI dataset, ANI1 dataset is also some real data, right? It's not the most fantastic model, but it's
Right.
principle usable for this as well.
Yeah. So the idea with this one was just so that I would have, like I said, something to play around with, where we, at least in theory going into this, I was like, oh, well, we probably know what the right answer is. Like, we know there should be single, double, and aromatic bonds and like the triples out here. But distinguishing those distributions and if those distributions are real.
But do you want to go after the lengths? Because you also have the force constants we have to figure out.
Yeah.
Like, the idea would be that you've got a whole bunch of force constants and lengths for bespoke
Mhm.
calculated molecules, and then you're trying to fit that, or would you go for after energetics directly, valence energetics
Yeah.
directly?
I think so in practice, this was me trying to just find distributions to make
Right.
the code work.
Right.
I think in reality, we're going to need both.
Okay.
But it might be a side question that's worth
Because that
investigating if we need both or what.
controls what kinds of data
Right.
sets we need to build up to parameterize from.
Yes, so there are ongoing questions, I think, in how much distinction you can get from any one of those pieces of data. So really, I have a lot of questions, and if people have ideas and thoughts, that's helpful. So, like I said, if we're going to work with those distributions, the initial idea was that if your SMIRKS patterns can divide your parameters into the same number of distributions, then that's what's ideal. But we need to somehow or other be able to split those distributions, and are they really normal, depending on the parameter. And then, like I was saying, 1 billion steps is sort of unreasonable. It takes us 3 or 4 days to do 10,000 on torsions, so on a CPU.
Do you know what the slow part is? Have you done any profiling to figure out?
So one thing I've done right now, we're keeping all of the chemical environments
Uh-huh.
instead of keeping SMIRKS patterns, which I think is memory intensive and could be, because they're so easily convertible, we could instead be storing SMIRKS patterns and then just create the chemical environment for the thing that you need. I did a little bit of looking on speed on that, and it would speed it up a little bit, but it doesn't seem to be.
If you're
slowest
going
thing.
back, especially many times, there's some
Yeah.
silly tricks like memoization that can just get ridiculously large
Mhm.
speed ups, where every time you ask to compute something that you've already pre-computed and pre-cached,
Yeah,
it's instantaneous essentially.
Okay.
So there might be some optimizations that might.
Yeah,
that would be
like,
relatively easy.
Yeah, if you have to code, I'm happy to look through it.
Okay,
Um,
yeah,
'cause,
it's
I
all
mean,
on GitHub. So
Yeah,
I can send you
memorize is like 10 lines of code. It's very simple.
Okay.
It's huge.
But there are general ways that some profiling might give us an idea about how to at least it's sometimes
speed up
easy
the
to get
computer
like 3
part.
orders of magnitude out of just fixing silly things that are
Right.
not supposed to be slow.
Yeah,
But then we can't go to 1 billion, obviously. That's not going to be a simple
Right.
code fix. That's going to be a different algorithm for.
right.
I mean,
Well,
you
and
can
it's-
avoid building the objects because like every single time you hit an object build in Python, it's going to take an actual microsecond.
Uh-huh.
And so that's probably dominating time.
So, okay. Well, so that's
You guys can talk.
okay.
Yeah.
So things to talk about.
Optimization.
I mean, this is really my last slide. So then the other questions within that are not just speeding up the code, but are there ways for us to make smarter chemical moves? Things I thought about was like you can use those decorators and see how prevalent they are within your molecules versus just saying we're going to consider all of them even if there are no fixed charges in your molecules. We're going to keep giving everything +0.
Mm.
So it'll keep getting accepted if there are no charges. Or if there's some way, instead of heuristically building that in based on the molecules, is there a way to learn those odds and adjust them as the simulation goes instead of
Mhm.
right now SMIRKY has uneven probability of making certain decisions, and those choices in probability were just some of Christopher, some of me going, this is what seems right based on what we have. So other things to think about.
I think there's huge potential to learn because this is completely new, as in capital N new. There's no precedent. It's really new territory. But some things that immediately spring to mind are combinations of atom and bond decorators. I'm kind of drilling down into the chemistry here, but
Yeah.
carbon, you can have 3 connections, you can have 4 connections. Kind of bond, you can have a single
Mhm.
bond and a double bond. But how many times can you have a carbon with 4 connections making a double bond?
Right.
It's illegal.
Right.
So I think there's real potential for identifying combinations which would greatly reduce your space.
Mm-hmm.
But this is where I think possibly a machine learning approach might help that, or some kind
Yeah.
of an analysis. Right now you're building up the first body of data that there is to try and inform that.
Mm-hmm.
But I think there's huge potential to make the chemical perception moves more efficient.
But I
I
think
agree.
it sounds like
Using a reference database would avoid this issue completely.
Using a what?
Using a reference real molecule database as a filter
Yeah.
when you're choosing a move, because that would not be a you would not see that in a real molecule
Well,
anyways.
So,
So the rule would say you would
But
reject the move.
but so right now, that's true.
That
So right
already
now,
happens,
that is
yeah.
a step. It's saying it'll make the SMIRKS pattern, and then it says you made something that doesn't match anything, reject it.
That's a good thing, right?
Right, that's a
Why
good
do
thing,
we-
but it
that's a
means we're
general
wasting a. But how many times are we wasting a move trying to put a double bond on a
Yeah,
carbon
yeah.
that has 4
You're
connections?
still, part of your billion moves is constructing tetrahedral carbons with double bonds, which is illegal.
Yeah. So
Yeah.
we should learn not to do that and remove it from the set essentially, or memorize it.
Or what you could do is try subsets of things. In other words, try 2 bonded atoms and see which 2 bonded atoms work, generate as
Yeah,
well, and that can give you subsets for
Yeah.
building up 3 carbon and 4 carbon chains and things like that. There's lots of potential
right.
here, but it's just like it's completely new territory.
Yeah. Well, and the other thing is SMIRKY right now is working on mini drug bank represents all of the chemical complexity in drug bank that matches permafrost. So it's trying to do all of that at once, where in reality you're probably not going to give it. Try to be like find all of the chemical perception for all of it. You're gonna say this is the. Like if you're able to break it up into steps, then you might be able to more creatively do
Yes.
those moves.
So-
So you won't have like you'll be like there aren't double bonds associated with this, so don't give it that.
We're trying to extrapolate from the way humans think about things, and in some cases, expert humans. So, expert humans can't wrap their heads around all of chemical space all at once. We tend to, block the matrix, and we'll just think about alkane kinds of things first. So there's an impulse to do that, and it will control the number of parameters from 300 or 600 down to a smaller number. But what do we actually need to do there?
Mhm.
How do we need to constrain it?
Mhm.
I've never thought about that.
Mhm.
Would it be, I don't know if I understand what's going on here well enough, so this may be a dumb question, but would it be possible to generate like the finest grain possible set of SMIRKs for your drug bank set, and then only go there and go to more general things?
Oh.
So you'd be working within a defined space?
I mean, but that would essentially type the whole molecule, right? I mean, you can get ridiculously specific.
Yeah, I don't have an
then you put
example
some-
in here, but SMIRKs can be like pages
Well,
long.
then maybe you put some
Just get more and more
upper limit on how complex
Yeah.
it can be,
Yeah.
but then type everything and then only generalize from there.
But I'm not sure how to take 2 really specific patterns and then generalize.
There's a great many SMIRKs patterns, some great many variations of SMIRKs patterns that can identify
Yeah.
the same fragment. So there's
Yeah.
not you could say, well, I've got, how do you know when you've got all the SMIRKs patterns, which might be, little atoms or fragments of SMIRKs patterns that you want to build up larger ones. It's
But
hard
it
to
might.
know when you've done enough, but in principle, you could probably do something. I think it would be.
But the idea of
So I
like
think we might be drilling down kind of deep right now for this status update section, and we want to fund some of this for the detailed planning parts.
Yeah.
John is so this you said this
oh
is
yeah,
one-
this is my last
okay.
slide I have.
So
Reviewed
is
acknowledgements.